So yeah, we're going to talk today about working projects with Don Shuyayu, who's a fellow graduate student at UCSB, and Yin Jia. And these are relatively recent results, so I'm excited to hear questions and comments. Great. So we are studying, as the title said, global dissenter. This is cosmologically relevant, more cosmologically relevant than ADS. And basically for two separate reasons. First, we're currently in an epoch of accelerated expansion. We have a tiny but positive cosmological constant, and we're going towards a dissenter-like geometry. Also, in the very early universe, there was a period of inflation, exponential rapid expansion of the universe. This is also known by dissenter. A key point in dissenter is that observers are part of the system. There's no boundary, so in AES we can move our observers to the asymptotic boundary. We don't need to consider them as part of the system, but here we really need to take that into consideration. And this is an old story people have known, but one of our motivations was this paper from Jeff, demonstrating that if you try to find the algebra of observables in the static patching dissenter, it's trivial and also you this observer. So that's a key point in what we do here. So our goal is to understand how well we can approximate QFT in curved space-time in global dissenter, including these observers. So observables that are defined relative to this field theoretic observers. Okay, so a little more precisely, what we're going to be doing, we're going to define states for our observables. Here we've written as alpha epsilon. Alpha are Fock basis states, they're in our QFT Hilbert space. And then this will be equal to this interval over this root region. This is called group averaging, and I'll introduce that in much more detail later. But we have this integration, and then we have a tensor product between our QFT Hilbert space basis states and then our observers. Great. And then using these states, we can define operators in our approximation here in perturbative gravity. So we have our standard QFT operators up here, defined as this summation, the alpha beta weighting the sum, and then when we go to this approximation where we include this observer in our state, we just modify these alpha and beta states, and now they are these states that we define up here, including the appearance.
So could you say again what the group is? Maybe I missed that.
I didn't. I'll talk about it later. It's a special orthogonal group. Great. So our perturbative gravity observables will look something like this, and then we want to understand how well we can reproduce correlators, or if we're taking inner products between these two defined states, how well do we approximate inner products in standard QFT in curved space-time, and we really want to understand what these corrections are and how they behave.
What is epsilon nave?
What is what, sorry?
Epsilon nave.
Epsilon, it's just the notation that we use. It's basically because there will be some small correction here.
It's not allowed in the state of the anything.
Yeah, it's, I think later I actually wrote it just as alpha and then sign-on instead. It's just denoting how we change these states and stuff. But yeah, it's just a notation.
Is it, so like, the way you written it is kind of like a projector on the observer degree of freedom, because there's only one sign-on.
Only one, sorry.
Like the phi hat PG,
Yeah.
it looks like it might be a projector on the observer degree of freedom. Is that important, or is that just some rotation?
Yes, we're only going to have, for now, one observer And so everything will be in one state, one observer
So
state.
the observer can have many states, right?
What's that?
The observer can have many states.
The observable will have many states, and then the
Observer,
observer,
yeah.
one state.
Okay.
Okay, so like we just saw, there's this group averaging procedure that we have to do. So I'll go into that in more detail. And then from there, we'll try actually inputting a specific observer state. So we're going to put one particle in the static patch. There will be a corresponding particle in the other static patch in the sitter. And then we'll try to see if we can, well, first we'll understand what our approximation, how good our approximation is there. And then we'll try a different state where we have more particles. Okay, so in gravity we have these so-called linearization instabilities, which essentially happen when we have solutions to our linearized Einstein's equations that do not correspond to solutions of the full Einstein equations. And these are known to occur for geometries where we have compact Cauchy slices and symmetries, joint symmetries. And both of these are present in de Sitter. So de Sitter is known to have these linearization instabilities where when we do linearized gravity, we don't necessarily get solutions to the full equations. Okay. We can avoid these instabilities if all of our conserved targets vanish. And this essentially means that our states need to be invariant under the background space-time symmetries, and then the operators, like the ones that we defined previously, will also need to be invariant under these background symmetries. Great, and this is basically just like a souped-up version of Gauss's law. Flux intervals have to vanish when there is no boundary, and we'll talk about that in an example in a second. Another way to say this is that these Kaplan symmetries are managed. So our generators annihilate states. These states need to be invariant under these gauge symmetries. Here's a list of a bunch of references. This has been talked about since the early 70s and then applied to de Sitter, I think, in the 90s. So there's a nice body of work on these. Okay, just quickly what we're doing, we have full quantum gravity, we're taking the limit as g goes to 0, we're driven quantum gravity, and then we're imposing these linearization stability constraints. I'll talk about how we impose them in a second. And we're including an observer and getting this approximate QFT in fixed de Sitter background. And then we just want to compare that to QFT, standard QFT in fixed background. Okay, so in de Sitter, these, as we mentioned, the question just a moment ago, the de Sitter group is the special orthogonal group, 1D. D is the space-time dimensions, and this group is non-compact. Higuchi showed in this paper that then this means that there's only one state that's invariant under all of the Kaplan symmetries, and that's the vacuum state. So we have the charges written up more explicitly here, just integrating over the Cauchy slice, sort of equivalent of the stress tensor in this Kaplan direction, and only our vacuum state 0 is vanishes under these charges. Okay, so that's not very useful. We'd like to be able to describe physics in de Sitter, and right now we only have one state in our basis. So we'd like to have a basis of more states, and to do this we use group averaging. And here I used square brackets to denote states in the original Hilbert space, and then we'll get a space of co-invariant states when we do this group averaging. So all this is represented as eta here, and then we're just integrating over this de Sitter group. DG is the harbinger on the de Sitter group. And great, now these capital size states that we defined will vanish under these charges. Yes?
The statement is that the only state which those either charges vanish is a binary. That's what you said, but it's not size or
state and the original colored space. that we have.
This is just a positional set.
Yeah, but this is like in QFT and curve space time, you have the like in a lock basis, it would just be just vacuum in the original colored space.
So you can extend the particle and then you can do a superposition by U of G. That's the state of the operation.
Yeah, this is a little different. These also aren't, I'll talk about it in a second, but they're not normalizable in the usual inner product, and we have to define a new inner product for these states.
Yeah, that was a question.
Okay.
Why do you call capital sign co-invariant? It looks invariant to me.
I think it's just it is invariant now. It's just the terminology because these invariant states are ones that are in our original colored space, and then we're building a space that co-invariant states. But they are invariant. Just
I see.
Is it E? Single.
yeah, just just to differentiate the pieces. Okay. Okay, so we, as I said previously, this is basically just Gauss's law. So we can see that in, we have a Maxwell field in a de Sitter background. So we have a global de Sitter here. We take a Cauchy slice and it's a sphere. And then if we have, say, in green, these positive charges, their flux lines will have no go. So they have to land on these negative charges, and total electric charge has to cancel. So in a de Sitter background where we have these compact Cauchy slices, total electric charge will have to vanish for any outer state. This group here is U1, and an easy representation for that is just complex numbers on this unit sphere. And then we can do this group averaging. So we'll get a co-invariant state by group averaging over some psi in our original Hilbert space that has charge Q. And here we put in our car measure, this D alpha. This is our U1. And then we see that this gives us a delta function at Q 0. So this is a projector into the Q equals 0 sector. And we really do now have states that all have 0 charge. Okay, so back to de Sitter with the full de Sitter group. We have our space of covariant states. As just mentioned, these are not normalizable in the usual inner product. You can kind of think of them as like generalized states, like plane waves in infinite space. So we're going to define a new or normalized inner product. These, basically the essential feature is you only have one of these group averaging procedures. So you have inner product between two covariant states is really the inner product between one covariant and one of your original basis states, and then you get your inner product.
Sorry, how do you know this is like group invariant or something? Because I imagine that the square bracket state can be acted on by group action, and now you may take one square bracket, one angle bracket. Like it seems I can have some group action acting on it and get a non-constant.
Yeah, so you mean the inner product?
Yeah. Like I would imagine it's more natural, at least for me, to have two of the square angle brackets. Then it's I think it's group invariant, but like now just one of them, how to make sure it's invariant under the symmetry of the Sitter space.
Yeah, you should just be able to check, put the group here, then you can include it in the integral, and it should be.
Okay.
The whole measure is both left and right invariant. So if you multiply either side to also one, but you actually.
Okay.
Great, so there was a lot of work trying to understand kind of how well this inner product converges, and here are some of the main papers for this. We had 2 papers, and the second one looking at a certain class of states in I think 2 and 4 dimensions, and then this paper from Don and Ian, for 2 papers, they looked at 1+1 dimensional consider, scalar fields, massive scalar fields there, and then another paper where they looked at general dimensions, scalar fields for different series representations, and showed that this converges as long as you have enough particles.
You mentioned the original vacuum was annihilated by the action. So do we have to put that one in by hand, or is it just not now in this new space?
The original vacuum. Part of the problem is usually this doesn't converge for the vacuum state, so usually we have to get rid of it. It's still there, so any state that that was invariant will still be in this co-invariant space, but because of this convergence property, we can only consider usually 2 or 3 particles per atom.
So should I think of this as you start the QFT and then you couple it to, let's say, gravity or whatever case symmetry you have, and then that restricts to a subset of states that satisfy Gauss law, but then you take G to 0 anyway. So at the end, you're just left, are these states, should I think of them as states of the QFT indicator, or is that, or are you defining your normalized inner product in some quantum field theory on this in the background, or in something which involves linearized gravity on the gravity, or is it just QFT?
Here it should include linearized gravitons.
Okay, so
maybe I need to ask you more to understand.
Full space, including everything, right? Linearized gravitons, full space.
okay.
And this, from the linearization stability constraints, you need everything to be invariant under the discrete group. So we'll need linearized gravitons. And then
So everybody will compare with the semi-classical gravity, including gravity, right? So then you can
Okay.
Okay, so I said that this converges for many states, and that's been studied pretty extensively. Proving that it's positive definite is a little more difficult, but there is this this idea from this paper here that shows that if you have a converging inner product on the space of covariance, then it's the unique inner product consistent with the star algebra on this Hilbert space of bounded operators. So this basically is saying that even if it's not positive definite, it will still be the unique inner product, and so there won't be a positive definite inner product in this space. Okay, great. So this is, if we're looking at these inner products, we want to understand these corrections away from QFT in a fixed background. So here, I think I mentioned this, I wrote these a little bit differently, but these are phi and phi prime are observables, and then psi naught are observers. And we have to do this group averaging for both of these, psi naught and phi. And then we want to understand what these corrections are. So we're going to call this psi naught, UG psi naught, our group averaging kernel, and we'd like it to approximate a delta function so that there are no corrections to so that we do just get the standard inner product. And we want to understand how closely it approximates this delta function. Okay. So first we can think about the behavior of this group averaging kernel at large G.
What is delta function? To reproduce original in product, it should be 1.
Yeah, it'll just, I mean, it'll give you G is 0, but there's no action on these feed prime and feed states.
I'm just saying, in order to reproduce in a product between 5 and 5 prime,
Yeah.
that combination should be 1.
It should be delta G.
Without any elements in
Like you're integrating over G and you want the right to just be, oh, sorry.
So in a product,
I see. I think in the second line you wanted it to be square brackets, not angle
Yeah, I
brackets.
guess there was maybe a little,
Because we wanted to reproduce the QFT in a product with no averaging.
Oh.
yes, sorry. Yeah, indeed, you want the standard result without this recorded. Okay. Perfect. Okay, so just briefly, their argument for how this behaves at large G, they decompose the de Sitter group into these U alpha, U gamma are rotations, and then doing the boost has some harm measure that has these extra factors of sig of lambda for every dimension. And then they use this set of rotationally invariant states, which are superpositions over n particle states. Each particle has some definite momentum. Great, so they use these states. They're rotationally invariant, so the rotation doesn't do anything, and we can just consider this sort of inner product between psi1, the boost generator, and psi2. For these states, they show that this vanishes exponentially. And they actually write out what A is, but this is kind of enough for what we're doing here. So we have control over the large behavior, or large G behavior of this quantity, and now we're just going to look at small G behavior. Okay. And like we said on the last slide, we wanted to approximate the delta function. We're going to restrict to 1 plus 1 dimensions. And then I just put one here. One way you can decompose this group, we're going to do it in a slightly different way and with a little more background, so a little more in depth. And then we're going to put one particle in the static patch and a particle in the other static patch and see how good the approximation is if that's your observer state. And then we'll see if we can do any better by adding more particles. Okay, so our de Sitter group in 1 plus 1 dimensions is isomorphic to SU2, so we can use ladder operators with the standard commutation relations, and then we can use these, get an auxiliary Hilbert space of eigenstates of this L naught operator. So these are given by delta M, eigenstates of L naught, and then ladder operators act as they usually do. They raise this M or lower by 1, and they're normalized. Great. So here the delta is giving the value of this quadratic passing here, delta times 1 minus delta, and we're going to focus on the principal series, where delta is 1/2 plus I mu. So this delta will correspond to our mass here, and little m is the state's angular momentum, since it's an eigenstate of mod. And here's a nice reference that looks at representations of SO1D, so in all dimensions. And then we can use this to study our de Sitter group. Basically get this from embedding into plus 1 Minkowski space. L naught is our rotation generator. You add the ladder operators to get one of the boosts, and then there's another boost where you subtract. Okay. And they're just shown here, rotation, and then each of the boosts just translated in. This is our theta coordinate, and this is our t coordinate. You can see the metric here in conformal coordinates, conformally flat, with this conformal factor 1 over cosine squared t. And then we can write down our Kelly vector fields in these coordinates. Okay, so we have our disorder group, and we write it in terms of our generators R, V1, and V2, like so. And then we're going to keep only small, only look up to order G squared. Okay. So what ends up being very helpful is instead of looking at the squared group averaging kernel, here again, these are supposed to be super brackets, I'm sorry. So here, the squared group averaging kernel, say we have one of these generators, J with parameter G, and we can find the Hessian for this squared kernel. And when we do that, it's a simple calculation, and it shows that we have, we get the variance of this generator J. Okay, so this, this Hessian, the values in the Hessian matrix are the variance of these generators, and these will be conjugate to the width of the squared kernel. So we can approximate it as a Gaussian, something like 1 minus chi, chi are going to be our eigenvalues of this Hessian, times g squared, and then this is something like the Gaussian. Our width, sigma, is equal to 1 over root 2 times these eigenvalues that we have. So we're going to use this idea to calculate our eigenvalues for our Hessian. The more negative these eigenvalues are, the larger their magnitude, the smaller the square is. So we're going to investigate how large our eigenvalues are in different limits and see how good we can make our approximation.
So that's the thing that's supposed to become a delta function?
Yes.
So is there a normalization? Is there some, those are proportional signs?
Yes, yeah, yours. Yeah, there would be some normalization, but it doesn't matter. Great, yes, so we want this to be a delta function. We want the width to be as small as possible. Just a comment that we're doing this squared kernel instead of the original loop averaging kernel. And technically there are some first order terms in G, but because we're adding particles 2 at a time in each static patch, these first order terms vanish. So it's okay to just consider this squared kernel.
So what was a chi?
Which one?
Chi.
Chi. It's these eigenvalues of this matrix, this Hessian matrix. So you're taking derivatives with respect to these parameters. There will also be cross terms here, so there will also be things like taking the derivative of theta and then the 1. And those will be off-diagonal terms. Yeah, maybe it'll be clear in a second because we'll do this with our state side one. So we're adding a particle in the center of the static patch. We have some normalization, and then we're taking a superposition over these basis states in our auxiliary Hilbert space, and we're doing some bounded superposition from minus m to m. Great. We have a particle on the other side patch. For now, we're just doing the calculations with one, and then we can generalize easily with the second one. And here's calculation of our squared kernel. It's not super illuminating, but we see we have this mu, the mass, and then depending on n, the maximum angular momentum of our state. Lambda 2 doesn't have any cross terms, but we do have some cross terms between R and V1.
Sorry, I missed the logic. So you have a particle in the static patch, that's the blue dot.
Yeah.
And then when you're superposing it into the other patch, or you're adding another particle, or what happened?
Adding another.
There's another particle. That's not drawn.
Yes.
And why do we need another particle in another patch?
You always need one to respect the symmetries.
I obviously want to. What's the other particle? Oh, you mean otherwise the state won't be disturbed, right? Okay.
And yeah, I should have said before, since we're in 1+1 dimension, we'll consider the conformal diagram looks a little different. But yeah, it's like unlocking the
Probably a stupid question, but adding a second particle makes it invariant into the boost. But what about the rotation?
Here actually, it's already invariant under, well, the expectation value of the rotation is 0.
Oh, okay, because sorry, I'm looking at carry over.
Yeah, and so you'll still, all your expectation values will be 0 when you have the other particle. The sign moments of the variances. Great, okay, so we have this underscore kernel, and we're going to take limits in a second, which will be a little more illuminating. All these other values are negative definite, and all of them grow with m, and mostly just see that in this fashion. So we're going to take the limit as n is large because we want large eigenvalues. We're going to keep mu fixed for now. That's a direction that we haven't really looked into yet, but that'll be interesting for future work. Okay, so we have fixed mu, we take large m, and then we get the eigenvalues of this Hessian. Great, so we have this V2 generator didn't have any cross terms, and so our eigenvalues remains the same. V2, it goes as minus m, and then we have these two eigenvectors that mix between R and V1. These aren't exactly what we get in the finite, or not finite, but small n limit, but then as we take n large, we get just R plus or minus V1. And those are shown here. And then these are proportional to minus m squared and minus m. Okay. So if we could take n to infinity, these eigenvalues would be infinite, negative, and then our widths would be infinitely small, and we have this delta function approximation. But we need to consider gravitational back reaction. If we take m too large, then there will be some back reaction on our state. So we need to understand that and have some cutoff for our angular momentum. Okay, so we're going to take m large but finite. We're going to have some cutoff determined by back reaction. We want to understand how good our approximation is if m cannot be infinitely large. So the idea here is we have this parameter lambda, say for one of our generators, one of the symmetries, and we want to understand if we change this by some amount, how does our squared kernel change? So this Gaussian, and we would like to restrict it to be within some accuracy. So only change by some small amount epsilon. And then we want to understand if we have this change in this lambda parameter, so this change in group space, how does that affect points in our space-time? So what's the space-time resolution? How far will the point move if we do this change in our parameter? This is just the space-time resolution L is just this change in parameter times the norm of our Kaplan vector. Okay, so we can plug in our delta lambda from this equation up on the top, and then we get a cutoff for how big the norm of our Kaplan vector field can be. And so this cutoff will be where you have your proportional to the square root of this eigenvalue. This eigenvalue, as we saw, will depend on capital N. So we'll take our space-time resolution to be order 1. Our accuracy is just some number, order 1, and then we get this square root relation. Great, so we're imposing a cutoff where the norm of our killing field is greater than these eigenvalues, the square root of these eigenvalues. Okay. Great, so with the second particle in the static pouch, as was mentioned before, you're exchanging some of the symmetry. So here we're exchanging the R plus B1 and R minus B1. So we really only need the better of these two cutoffs. So the eigenvalue that went as minus m squared. Great, and then we can draw pictures where this cutoff should be. This is just some fixed value of n for each of these, and then we can put them all together. The region where we have a good approximation is in between these cutoffs, and then past these cutoffs, our approximation is bad. Points will move too far to be accurate, or our squared group averaging kernel does not approximate delta function as well. Okay, so this was just a summary of the end, putting it in and finding these cutoffs. Now we want to understand what the largest value of n we can choose, and this is when we think about back reaction. Okay. So, I miss it.
40 minutes, it's been 40 minutes, a little less than 40 minutes, and then so.
Perfect.
Or you can reuse a little bit long.
Okay. Thank you. Great, so we're looking at back reaction to put a cutoff on M, our angular momentum, and thinking about back reaction, there's a nice argument from this paper from Steve Giddings and Don from 2007, where they put a limit when back reaction becomes too large. So they start with rotationally invariant states, and this will give a preferred foliation of de Sitter space by spheres, where they'll be large and then at the neck shrinking and then larger again. And the back reaction will be largest at this neck region. For us, that's the t equals 0 place, and then this will be controlled. This back reaction is controlled by the energy flux through that neck. So our energy flux integrating over the neck, the stress tensor in the normal direction of this t equals 0 slice. And here they estimate that back reaction will be small until this energy flux is a quarter 1 over g. Okay, so that's how we want to limit our energy flux. Where this holds for global de Sitter, if we just wanted to consider the static patch, then we can maybe impose a less rigid bound. But here we really want our approximation to be good in all of de Sitter. Okay, so then we can estimate what this energy flux should be for our observer state. The time derivative of our metric vanishes at t equals 0. And so our creation and annihilation operators, our positive and negative frequency modes, are the same as in a static cylinder spacetime. So this F is like the Hamiltonian of the energy in this static spacetime. And great, so then we just have to consider the energy of these particles, and that will give us an estimation of F. And this is just the standard square root m squared. Here m is mass now, again, mass squared plus j squared, the angular momentum, and this will give us estimate for our energy flux near t equals 0. So these are for particles that, like the state that we have here, are at the t equals 0 point. Okay, great, so now our energy is bound by this 1 over g. So our maximum angular momentum R. This gives us our limit on angular momentum corresponds to capital M. So we're limiting 1 over g. And then we can use this relationship that we had, find at theta equals 0 what the value of proper time is for our cutoffs, for our this expression for our norm of our field vector field. And then we do that calculation and we get this result of the proper time between our two cutoffs is log of 1 over g squared. And then from here, because de Sitter expands exponentially in time, we'll get a space-time value of 1 over g squared. And this really does cut off some significant portion of de Sitter, top and bottom here. So we wanted to see if maybe we could do better, if we could get a better approximation of QFT curved spacetime with maybe different observers. Yeah.
What is the relationship between the curves and in this plot?
Yeah, so these curves are just these contours where the norm of the Killing field is equal to the square root of these eigenvalues, and then these for they were different for the different cutoffs. So this one's the B2 cutoff, and that one is M, and then both of these, the orange and the blue ones, go as M squared.
Why is it that it's the sort of lowest down curves that are cutting it off? The curves are because you have multiple particles and they sort of cut off different points, but I would have thought, like, if you have both of those particles acting as an observer, then it would make the region that behaves nicely bigger. I'm maybe being very naive here.
It does. So originally, with one particle, I think this blue one was bigger, and then now with two particles, the cutoff is the same for the blue and the orange ones.
But that seems smaller than just say the blue and the blue ones.
Then which ones? Sorry.
So if I have one particle, wouldn't it just be the cutoff would just be the blue lines? Which seems.
Oh, I see.
I would have hoped you'd get like the outer one of the blue and the orange rather than the inner ones. So it's like a larger region because we have multiple particles we can use. I'm just slightly confused why we sort of need, it's like we need all the particles to give a double function rather than just one of them.
Yeah, so we need our we need the squared kernel to be Gaussian in each of the generators in order to get this delta function approximation.
Okay, and so with one particle it just wasn't Gaussian?
Yeah, well, like for one particle, like in this region, it's not. In that, whatever the orange generator is, so like R minus V1.
Okay, I think that's...
Great. Okay, so now we're changing our observer state and seeing if we can do any better. And in particular, we'd like to see if maybe we can do better within the static patch, and potentially with some trade-off that our approximation no longer works in as much of the region outside of the static patch. Great. So we want to see if we can do this, get some better control by inserting more particles. Here we do it along the theta 0 geodesic. We have our first particle here in blue, and then we're just doing time evolution on that to get particles at different times, and that's given by the V2 is our static patching algorithm. Okay. Great. So we're we're doing very similar calculation, calculating the squared kernel. Now, because we have this time evolution, we need to compute things like what's shown here, where we have these time translations. But here, this Baker-Campbell-Hausdorff problem reduces really nicely, so it's not too much extra work. Our B2 always computes with these, and then R plus B1, R minus B1, just get an extra factor of e to the t, either plus or minus t. Okay, so we'll calculate our squared kernel as we did before, and then we're going to take the large n limit because, again, the magnitude of each of our eigenvalues grows with m. So we take this limit and we get basically same thing we got for the B2 eigenvalue, now for 3 of them. And then for our R plus or minus B1, we now are dependent on this time for these boost particles. So the eigenvectors here all remain the same in the large n limit. And as I said, these will now grow with t. Again, this approximation works perfectly if we can take n to infinity. And now, for these two eigenvalues, when we take t to infinity. But back reaction is also going to limit how far we can evolve these particles. And so we'll have some trade-off between large n and large t.
Sorry, what? Taking t large will help like plus and minus, right? It will be
So that's fine. Yeah, here. If we wanted better control in the static patch, this is the cutoff for B2, so it's okay. We still had n set by 1 over g. This would still be a more significant cutoff, but we could maybe have better control within the static patch. Great. Yes, so now that would be great if we could take t to infinity, but it's also going to be bounded by back reaction. Okay. So now we need to estimate what our energy flux is at t equals 0. Again, we'll have one particle localized at t equals 0, so it just gives this square root m equals j squared energy flux. And then for our particles that are away from t equals 0, we have to evolve them back in time. We can take the limit where our particle is relativistic, so something like mass of order 1 and our angular momentum order 1 over g. And in this limit, this time evolution acts like a boost. So this boost will change the energy of these particles. It'll introduce a factor of e to plus or minus t. Great. Yeah, we could consider other limits, but it seems to work out in the same way. And then we get something like this, where we still have the same dependence on the angular momentum, and now we get these factors of e to the t from each of the 3 particles. So this will now be something like n e to the t, and this is bound by 1 over g. Okay, so we potentially have some trade-off in the behavior of n and t, and maybe this could give us a little more room in our approximation. At theta equals 0, we can again estimate this t star, the time of our where our cutoff surface lies, and this gives us log m squared e to the 2t, and so this n e to the t bounded by 1 over g, this will be bounded by 1 over g squared. It doesn't really matter how we do this trade-off, we get the same limit either way, and it's the exact same limit that we had before. So something like log 1 over g squared, and our space-time volume is going to be exponentially that, so 1 over g squared. Okay, any questions before? Okay, so looks like we couldn't really do too much better. Possible maybe with other observer states, we could find something different, and that's still something we can look into. Another thing that's a work in progress is trying to understand correlators in this approximation. Here we have our correlator of these perturbative gravity observables. Here we integrate over, call these F functions. There's something like Gaussians, and each of them are orthogonal, and we keep them bounded within some proper time t. And the idea here is how well does this correlator approximate the standard QFT correlators? How large can we make this proper time before we can no longer approximate these correlators up to some accuracy? Okay. And these F functions are here. Basically, they're helpful in certain circumstances, like if you have x1 and x2 null separated, then this correlator should grow to infinity, should diverge, but our perturbative gravity correlators won't. So you get some control by including these Gaussians. And it's essentially something like a UV cutoff, but we can, it can change depending on our observer state, it can change with location. And yes, that's still a work in progress, but another way to try to understand this cutoff, this proper time cutoff. The hypothesis is that this would just decrease the amount of volume, so we wouldn't get any more in this approximation. Okay, so some other future directions. I mentioned this briefly. You can consider large mass, large mu behavior. This is also bounded by 1 over g, but maybe the way that our cutoffs depend on mu is different. We would really like to see if there's any implication for inflationary cosmology, going to cosmological coordinates, and then seeing if this says anything about how well the approximation holds if you have some number of e-foldings, or if it doesn't matter if you're in the de Sitter vacuum. So that's something we still would like to think about. Going to higher dimensions, that should pretty much give us the same results, except now we need to consider these larger symmetry algebras, so just some technical difficulties there. And then mention this quickly too, we could change our observer states. So we could do something similar to what we've done before. Maybe if we had other superpositions, maybe our eigenvalues would go as higher powers of the angular momentum. Perhaps considering coherent states instead. And this last one's just part of our original motivation was these von Neumann algebras. Maybe there's something you would say, but I'm not sure. Okay, and then just to summarize, we have in de Sitter linearization stability constraints. So we need to group average over our states in de Sitter. We include an observer in these states, and then we chose certain states for these observers. So a particle in the center of the patch, and then particles at different times. Our space-time volume was order 1 over g squared, and we couldn't seem to do much better than that. Thank you.
So could you say maybe a little more concretely what you think happens when the QFT prediction breaks down? So in particular, I'm wondering, so you say it's like a power series in 1 over g, and so I guess it should be a dimensionless parameter. So is it like the de Sitter length in units of g, or the mass of something in the correlator, or and do you have some sense of, could you calculate the form of the correction? In this setup, I mean.
Yeah, I think our correlator calculation will give us something that's a little more concrete of how this looks. The intuitive picture is that, like if you had states that are past this cutoff, they'll be heavily smeared. So like any point will be moved too far by these de Sitter symmetries. So things that, observables that are originally orthogonal will now have some overlap. Yeah, that's mostly what's going on in this approximation.
And the dimensionless expansion parameter, is it
So
G?
here is 2 dimensions. G itself is the
Oh, it's just, yeah, it's in 2D, okay. I see.
Yeah, could you maybe like explain again? I think this goes back to like how we introduce the cutoff. What is the reason of introducing this cutoff? If I only have the cutoff, what goes wrong? I mean, I'm trying to understand what's valid in this volume 1 over G squared, what's not valid. Sorry. Well, what is going to be wrong if you go away from this 1 over G squared? Yeah, like why do you introduce the cutoff in the first place? Can you remind me a bit again?
1 over big G squared?
No, like just why you need the cutoff. I mean, it seems like you have the cutoff, you add a volume to 1 over G squared, and then just going back, why do you actually need this cutoff? Like what goes wrong if you don't?
Yeah,
have the
it's
cutoff?
basically what I said before, that now if you have 2 observables in de Sitter and then pass these cutoffs, then you kind of distinguish the states between them. They'll be moved. It's basically that the points above there are moved farther by these killing symmetries.
So, past and future infinity, the symmetries are moving points infinitely fast, and so even if you have some very tiny peak Gaussian, they're still getting moved like more than the cis length.
Yeah. Yeah, more than whatever the resolution is.
So this, this kind of movement is kind of built in your setup of this group integration, right?
Yes, I mean it's happening because we have this.
Okay,
this
okay.
repetition.
It's morally, the cutoff is relative to the location of the particle, right? You have the particle you're using, so if you had another particle that was like way up in the future, then you sort of had 2 patches that were
Yes.
under
yeah.
control, like the original one and something way in the future.
Yes. Yeah. Yeah, but part of the problem here is that
If you had 2 observable, 2 particles that are like, or you had 3 particles, if you move them so that one goes with part of the past and one with part of the future, wouldn't that sort of end up? Oh, I guess the point is that they need to propagate through the middle somehow.
yes, yeah, it's because you have
They need to make
too
it
much
to its
matter.
road, you have, I see.
Yeah, so there are, when you say that the overlaps become different from QFT, there's like sort of non-perturbatively small overlaps that build up like inside a black hole, which like a bulk observer can't see. And then there is also like correlation functions change at some polynomial order in G, which bulk observer can see. Which one are you seeing? Is it the first type or second type?
I believe it's the second type.
Okay.
Talk more about here, what you mean about the first one. But I believe it's-
And yeah, so you're saying that like the change in some correlator actually competes with the original correlator.
Yes.
Okay. Yes, sir. Thank you.
Okay, let's thank Molly again.